Good afternoon, everybody. My name is Oliver Gould, and today seemed like a good opportunity to talk through some highlights of the resource-efficient manufacturing project, or greatest hits, if you will. So, why resource-efficient manufacturing? Resource consumption is unsustainable, and improvements to date have typically been incremental. And how do we want to do this? We want to support, as Shahim was saying, we want to move towards radical systemic improvements to reduce environmental impact and improve resilience to the consequences of these diminishing resources. And what have we done about this? We've developed some assessment methodologies, some strategy implementation tools, and we've illustrated these with case studies. And today I'm going to race through quickly describe the methodologies, some of the tools, and quickly go through some of the case studies just to give you an idea of what we've done. So, talking about resource-efficient manufacturing, we initially focused in on materials. And why did we focus on materials? Basically because products are material goods. They're the key resource. Not only that, but they define the resource consumption and thus efficiency of energy and water. And finally, bottom line, they're a significant share of production cost, up to 50%. So to improve material efficiency in manufacturing, what can manufacturers do? What's their sphere of influence? We narrowed it down to two areas that they can look at: product design, or they can look at production design and operations. So that's how the things are made. And we've got a few example strategies that can be used to improve these the material efficiency in these two realms. This was our plan for designing the decision support tools to help with these strategy implementations. So we've divided it into design and production, and we've come up with a design for material efficiency methodology and material flow assessment for manufacturing systems. And these link up to the strategies that I mentioned before. One of the key things to remember about material flow or think about is that previously material flow has been well measured in quantitative terms. So based on a mass balance, conservation of mass, and inputs and outputs of different processes are quantified. We identified that qualitative data was a challenge, and this is based on the fact that materials, as they go through different processes, they undergo transformations. Therefore, these qualitative changes happen, and these properties are not necessarily conserved, as you may imagine. The qualitative factors also are the key things to describe the environmental impact of a process or material and define what can be done with it, the improvement opportunities. So the qualitative data is the thing that kind of gives meaning to the quantitative data that you already model. So going on to the material flow assessment, that's for looking at production. We developed a framework that allows you to model the flow and define and improve performance. So you define the model of material flow in qualitative and quantitative terms. You then assess the efficiency and the impacts, and then look at ways of implementing some strategies to make improvements using some simulation tools or whatever. So some of you may have seen this before. This is a quick case study to describe one of the ways that you could improve a manufacturing system, and this is a bottled drink manufacturing system. Oops. So we've got a number of bottling processes, and importantly, we've got three different parameters, one of which is qualitative, and that is the process dependency. What kind of position a process can take in a sequence of events. And then there's two quantitative parameters. There's the process efficiency, the reject rate, and then the basic input-output mass flow from each process. So we developed a tool in MATLAB with my assistance from my colleague Alessandro to basically find the best sequence of events that will give you the minimum amount of waste produced and also the minimum impact of waste produced. So just quickly, the data, qualitative and quantitative process information for those processes. You input the process information for each one, and then some calculations happen and things, and it kicks out the permutations that a process, that a production can take. So here, this graph shows the cumulative waste for 3 different process sequence permutations, which in this case were the 3 processes permutations that were allowed. And in this case, the process permutation B was the one that produced the least amount of waste cumulatively and the greater proportion of waste which was had minimized complexity and therefore a bit easier to recycle. So moving on from process sequencing, and then we're going to go on to a Unilever production system, which I will describe 2 separate implementations that we carried out for this. So it's in the same Unilever production system, and we carried out the material flow assessment, and broadly we find that there are multiple products and relatively few processes. And very much related to CIP, the resource consumption is very variable at changeover and can be very high in some cases. So the changeover between one product and another can therefore define the resource consumption, water, energy, materials, time, and this was defined by a qualitative material flow, and this was the potentially cross-contaminating materials that were within these different products. So again, with assistance from my colleague Alessandro, we developed a scenario modeling tool which gives you resource-efficient scheduling, and this utilized a genetic algorithm amongst other calculations. So take the order, say 50 products. The tool calculates a source-destination matrix and then calculates the minimum resource consumption path to produce all those 50 products. So here we have an optimized production schedule which gives you minimized changeover resource consumption. But can we avoid these 2 higher consumption changeovers? And we think we can. By eliminating the resource-intensive changeovers, we wanted to change the design of the processes. So again, we used some intelligent computation methods to inform process design. And here, we examined the full inventory of products that they produce, and we carried out some k-means clustering of this inventory. And what this did was it gave you different clusters in which to divide up this inventory. So on the first bars, we've got 1 cluster, which is all the products. Second, we've got 2 different clusters. Third bar, 3 different clusters, and fourth, and so on. We then applied the scheduling algorithms. So we applied genetic algorithm as well as ant colony optimization of the product sequence. And we found that having 2 different clusters, that's 2 different groups of the full inventory, with an ant colony optimization gives you the best opportunity to eliminate these resource-intensive changeovers. So I'll just go on to, this is just a description of the 2 clusters. And here we've drafted out some ideas of how you might achieve production of these 2 different clusters of products. because obviously you don't want to just build a second production line, because that would be very overly overkill for the capex and things like this. So we've come up with the original processing system for the biggest cluster, and then for the smaller cluster we've got an alternative design proposed. So the optimization of the scheduling can minimize the resource intensive changeovers, but then if you alter the process design, there's a possibility of eliminating them entirely. Finally, going on to the design, product design for material efficiency. I'm just going to go through a few of the different tools that we've come up with, and then a quick example of them in the case study. So interventions with product design have scope for radical improvement in material efficiency, but that scope comes hand in hand with some complex decision making. So the first thing we did was we looked at the three different strategies that are fairly well known, and we came up with a hierarchy for these and exploded them a bit and came up with a bit more detail to them. So at the top we have material elimination, followed by material minimization, and finally material substitution. To help us to understand some of the parameters relating to materials in a bit more detail, and we developed these material efficiency factors. So this is a way of measuring and managing and improving the performance of your material decision making, basically, in design. So these balance qualitative and quantitative descriptions across the life cycle. And you can see that there are 9 different factors that we came up with that go across the life cycle. Conveniently, these can fit onto a kind of spider diagram for visualization, and this gives you a quick idea of the performance of a material within a product. So quickly just going to go through a case study of just a bicycle. And we developed a methodology for looking at a product and assessing it systematically. And on the left-hand side, you can see that there are 4 main steps to this. So to begin with, you set the assessment boundary. Within the assessment boundary, you then pull out your material inventory. So those are the materials that you want to look at within your product. You then carry out a material efficiency assessment of those materials using those factors that I was talking about before. And then finally, you can look into implementing a strategy. So you use the hierarchy, material efficiency strategy hierarchy, and then that helps you to decide which kind of strategy you want to go for. In this case, for the bicycle, material substitution was chosen. And then a few substitute materials were assessed for their material efficiency in comparison with the original material. So this is just a quick description of how this design for material efficiency methodology could look and be applied to a simple product. We've got another case study of a slightly more complicated and technical product, but I'm not going to go through that today. It's a photovoltaic panel, but it'll be in the paper that's coming out soon, hopefully. So, in conclusion, just a bit of a breakdown of the project highlights, really. We looked at material flow assessment in manufacturing systems, and we came up with a design for material efficiency methodology. We came up with a number of implementation tools that help you to use the strategies available, and then we gave them a little bit of context in terms of some case studies and some industrial partner case studies. So thank you very much, and I'll answer some questions later on probably.